Hi there and welcome from Ventura, California to today's webinar, Applying GNSS Interference Detection Inside and Out, sponsored by InsideGNSS, NovAtel, and Inside Unmanned Systems, and hosted by WebAttract, the leaders in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the current state of GNSS interference. Now, we've invited you, along with over 400 professionals across 52 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get going, Richard Fisher, publisher at InsideGNSS and Inside Unmanned Systems, would like to take just a moment to welcome you and introduce General Poss, who will be moderating the main portion of today's webinar. So over to you, Richard.
Thanks so much, Lori. On behalf of the InsideGNSS and Inside Unmanned Systems team, I'd like to extend a warm welcome to our international audience for today's webinar. We're delighted everybody can join us today. In just a few minutes, our panel of experts will provide what is essentially a virtual workshop on various types of interference detection, and tools to identify sources of hidden interference. In a short time, they will take us from the theoretical to the very practical. Now, I'd like to turn the webinar over to today's moderator, General James Poss. General Poss is the Chief Executive Officer of ISR Ideas, an intelligence, unmanned aerial systems, and cyber consulting firm. He is the founder and former Executive Director of the Alliance for System Safety of UAS through Research Excellence, known as ASSURE, which is the FAA's Center of Excellence for Unmanned Research. He's also a 30-year U.S. Air Force veteran with combat experience in 4 wars and was the Air Force's Senior Career Intelligence Officer at his transition from active service in March 2013. General Poss has extensive experience in cyber operations from his assignments with the National Security Agency and as the Air Force lead for the stand-up of U.S. Cyber Command. General Poss is going to set the table for today's discussion, and I want to thank him for joining us today. General Poss.
Well, Richard, thank you for that overly kind introduction there. I'll try to live up to it. Okay, so I'm going to tee everybody up for what we're going to be talking about today, which is GPS interference here. But before we do this, I think it's appropriate to kind of set the stage and figure out what everybody's experience is with interference before. So we got our first question up here, and it's a pretty simple one. Have you experienced GPS interference before? Yes, no, or not sure. So, Lori, go ahead and let's turn this on and get answers back from our audience. I don't want to mess with the results, but there's clearly one answer that stands out amongst the other 3. We'll see if I'm right. I'm not going to tell you which one it is. All
right, let's see. There we go. Well, we got 70% saying yes, 12% no, 18% not sure. So how did that stack up?
Yeah, no, I would have gone with not sure because I think there's a lot of folks out there that think they got interference that probably did. But, you know, I tell you what, my experience in the Air Force was there were all types of interference sources that you never knew in a lot of cases just because we didn't have advanced software and techniques like we're going to be talking about today. So a lot of confident people out there. We'll see if that holds up throughout the talk here. All right. Okay. So the first one, I'm going to kind of set the stage here, and I kind of titled it jokingly, GPS, who knew it was so vulnerable? And the answer is we knew it was vulnerable to begin with. But let me give you a little GPS history. As most of you know, it was invented by the United States Air Force. This is normally where I pause the whole webinar and ask for everyone to thank the Air Force for inventing this. I won't do this time, but next time we will. And the objective we had for inventing GPS was, you know, what was a military one. We wanted to strike anywhere, anytime with tremendous accuracy. Believe it or not, Plan A was to use our cruise missiles in what we call TERCOM, or terrain comparison, which is where we would map the whole Earth and map it down to about 3 to 5 meter accuracy, and the cruise missiles would have a map of where they were going in their tiny computer brain, and they would compare that map with what they were seeing, and they would navigate to wherever they wanted to. The accuracy was you had worldwide coverage. It was pretty darn good accuracy. The bad part was you had to image the whole Earth, and every time somebody put up a another building or something like that, you're in danger of smashing into it. So what we did was went with Plan B. Plan B sounds a little crazy when you say it out loud, but we were going to put about 24-ish satellites in mid-Earth orbit, give everybody a GPS receiver, and hope that no one jams a signal. And the pros are, everybody knows the pros. Worldwide coverage, absolutely amazing accuracy. The cons are it's relatively low power because these things are satellites. You can't hook them up to a nuclear power plant. They orbit at 12,000 miles. They're going about 8,700 miles per hour. Do the math. So it is pretty easy to jam and interfere with the signal, which worried us from the get-go in the United States Air Force. So much so that we started to train intensively on what to do without GPS in about the mid-90s or so. It was a lot harder than we thought. We had to get a tremendous amount of permission to do this. And finally, in the mid-90s, we finally got permission to do it. We did it out at the absolutely massive Nellis Range complex that you could see there. Down in the lower right-hand corner, the infamous 98 range wing guys, the Gomers. They read the Riot Act. You have to always keep your eye on the Gomers because they are the world's best air defense guys, and you can't always trust them not to do something nefarious. They probably capture that F-22 that's in the middle of them there. We warned the FAA, we warned the Highway Patrol, we warned everybody. The result was just about everybody trusted their GPS and died horribly to those guys in the lower right-hand corner first couple of missions. That was fairly predictable. The unpredictable part was there was no ATM, gas pumps, weather reports for miles because we had no idea that those kind of people were relying on GPS. So our intentional interference had the expected results during the exercise with the participants and unintended results with a whole slew of people that we had no idea was using that. We've since fixed that, by the way. Okay, so from then on out, no one trusted GPS. Everybody was checking for jamming and meakening, which is a technique where you slowly draw off the position of a navigation aid. And as a result, GPS interference reports skyrocketed. Believe it or not, in the Air Force, the intel guys get stuck with investigating a lot of those. So our guys were investigating a lot of these interference reports, and we expected that, of course, there was, sleeper agents from Al-Qaeda or whatever out there with powerful jammers. Turns out that, no kidding, cigarette charger GPS jammers are a thing, that you can buy them on the internet, and there's all kind of jammers out there. And I guarantee you, if you're a bozo and you have some type of emitting device that puts out RF energy, you're going to take out a chunk of that GPS. So it turned out to be a really big problem, both nationally and internationally. Around the world, unintentional GPS interference was a big deal and is a big deal in the Air Force. All right, so that's my story, and I am sticking with it. And now for a much more technical and well-educated view on what to do about GPS interference or how to detect it, I'm going to turn first to Sandy Kennedy. Sandy got her master's degree from the Department of Geomatics Engineering at the University of Calgary in 2002. She worked after graduating briefly in inertial surveying for pipeline inspection before she realized that she missed GPS. She joined NovAtel's research group in 2004, just in time to follow the SPAN GPS INS technology into productization, which remained her focus until 2013. This is when she moved into her current role as chief engineer of receiver cards. Her primary motivation is bringing new positioning and navigation capabilities to the marketplace and to be put to use in real-world applications. So I'm going to turn it over to you, Sandy, and take it away.
Great. Thanks very much, General Paz. All right. Well, thanks for joining us today as we talk about GNSS interference detection inside and out. So when we were planning our OEM7 generation of precise GNSS receivers, we knew it was time to introduce interference detection and mitigation capability. Interference effects can be difficult to diagnose and complicated to track down. And we've learned this in our own developments and from supporting customers over a diverse range of applications and geographic locations for more than 20 years. I mean, as we all know, GNSS offers amazing positioning and timing capabilities, but it's predicated on a very weak signal and a complex signal processing chain with multiple entry points for interference. So serious GNSS users need a way to identify and deal with interference on their own. We've also learned that many folks are either not willing or able to share all the details of their application or the system that they're building our receivers into. So they really need a way to deal with it by themselves. And I also like to joke that interference is something that a buddy of yours has had to deal with, but never you yourself, of course. So with that in mind, I thought I would share what my first experience with interference was at a really practical level, where I encountered it with a customer, and it wasn't just, you know, a topic in a grad course that I was taking. So it was back in 2005, and I was working on the SPAN GNSS INS product line then, and one of our major customers was Sport Vision. And if anyone's watched NovAtel presentations before, we mentioned Sport Vision a lot because they were a fun customer to work with, and it's something that is pretty recognizable for people too. So they needed to position NASCAR race cars continuously with low latency and at the highest possible accuracy to be able to enhance the video broadcast of the race. So to be able to point that arrow at the right car, they needed RTK levels of positioning. And they'd already upgraded to GPS INS because the NASCAR track is generally a fairly difficult environment to maintain RTK positioning in. You've got highly banked turns that make you drop satellites in and out of your solution. There's often a chain link fence that sort of arches over the track to protect the spectators from any bits of car that might be flying into the stands after a crash. And there's often stands that the spectators are sitting in that effectively enforce a high elevation mask on parts of the track as well. So we had the system up and running for a while, and then they were working at the Daytona track, and Sport Vision noticed that on turn 1, they always lost RTK positioning, and they often lost all GPS positioning. So yeah, I guess I do have to confirm it was just GPS back then. It wasn't a GNSS system then. And these guys are pretty savvy users, and they'd worked through all of the obvious things to try to debug what was going on turn 1. So the first one was, you know, okay, I'm losing RTK positioning. Does that mean I'm not getting differential corrections? Is there something the matter with my telemetry link that's sending me my RTK corrections? And no, that wasn't the case. They had tried to figure out if it was specific to one car or one receiver because they had multiple systems. So they swapped it around and run it multiple times, and it perfectly repeatable. Didn't matter what receiver or what car they were looking at. So they logged a data set. They had the capability to do that, and they sent that data set for us to analyze. And we walked through it, and everything that we could see was working properly. We were looking at how the INS was accepting updates. We were looking at the GPS tracking, and yeah, sure enough, the CNOs looked a bit low. But beyond that, we really had no way on board the receiver at that time to be able to say what was going on. So Sport Vision, being very savvy GNSS users, and really, I guess you should call them RF specialists, they searched the area around turn 1 with a spectrum analyzer attached to an active GPS antenna. So after, you know, some hours of driving around with a golf cart and this rigged up spectrum analyzer, they found their interferer. And it turned out that it was on a luxury RV that was in the camping area around the track. And on that luxury RV was a satellite TV antenna that had a design defect that made it an accidental emitter on GPS L1. So it was an unexpected thing to find. I mean, satellite TV should have been okay, should have not been a problem with our part of the spectrum. But like I said, an unintentional interferer here, design defect that was creating a fairly effective jammer on turn 1 there. So I look back at this, and that was a really stressful situation. And we spent a lot of time on both sides hunting this down. And it was really a best case scenario in terms of debugging. I mean, NovAtel and SportVision had a great working relationship. SportVision was willing and able to provide data sets. They had used our product before, and they had confidence that our product, did work and did work well. And they were very smart users with a lot of RF experience and had specialized equipment like a spectrum analyzer. And they had full access to the area that they were working in, no private property restrictions or anything like that. So looking back at this now, this was really a seminal experience. I remember the sweat and the anxiety around trying to make this work, both for SportVision, trying to make it work for their customer, and for NovAtel, trying to make things work for our customer there. And I remember thinking then, there really has to be a better way to do this. And now there is. With our OEM7 generation, we introduced something called the Interference Toolkit. So the Interference Toolkit has two major areas of functionality: detection and mitigation. So we provide the mitigation capability to every user, no matter what the purchase model is. And the mitigation capability is a specific option for situations where you can't eliminate the interferer from your operating environment. So I'll start by going over the interference detection capabilities built into every OEM7 receiver. And here's pictures of all our OEM7 receivers. In the back here is the 729 and 719, which are our traditional form factors used in the 628 and 615, and actually made popular previously with the OEM7 generation. So those are sort of our backwards compatible, meant to be a bit of a drop-in replacement for a 615 or 628. And then we have our newer form factors here, the 7700, 7720, which is a dual antenna input for a heading solution, and the 7600, our smallest form factor card over there. And those three new receivers all use this high-density 60-pin digital connector right here. So on all of these receivers, we offer spectral analysis capability, which means we let you view the power spectrum seen by the receiver. And this part we share with the user, and we also use it internally. So because interpreting power spectrum plots is a bit of an art, and it's not really well suited to real-time operation as a human doing the interpreting anyway, and it's also not the only indicator of interference. We run proprietary detection routines by default on board the receiver. And those routines are relying on many different data sources unique to the receiver that give an indication of interference. So as we look at all those different factors, we can come up with sort of a signature for the different types of interference. And when we detect something, we automatically warn you. And how do we automatically warn you? Well, we put we set a bit in the RX status word that's in the header of every NovAtel format message that we output. So I really struggled with a good way to show this in a slide because it's really hard to make an interesting looking slide out of RX status word, but I felt compelled to tell you about it because it's a really, really handy thing. So the RX status word there that we've circled in red is in the header of every NovAtel format log that's output. It's an 8-digit hexadecimal number that you decode into 32 different status bits. So it's sort of hard for a human to do, but it's not so hard to code into your message parser or to have interpreted by Connect, which is our PC-based utility. So here on the first example here, best pause is a pretty common log that people are pulling out of the receiver. And in this case, on the top here, all zeros is good on an RX status for us. And then here, you can see this is what it looks like when you've got bit 15 of your RX status set. And bit 15 is reserved to indicate jammer, and jammer detected if it's set to 1. So if you ask for the full RX status log, you can dig a little bit deeper and get a little bit more information. We'll tell you which RF path the jammer has been found on, L1, L2, or L5, for example. And you can dig even deeper than that and request some logs from us, like IT detect status, which will tell you the frequency, location, power, and bandwidth of the detected interferer. So that's running all the time in the background for you on your receivers, like a built-in test to let you know if we're seeing anything unusual that would not be considered normal and healthy for the GNSS signals that you're tracking. Okay, but maybe you really like interpreting power spectrum plots. Like, they're really cool, you can see lots of interesting things in them, and you might be looking at very fine details, especially if you're a system integrator. So in addition to those detection routines, you can, that are always running in the background, we let you view the power spectrum as seen by the receiver in 3 different points in the signal processing chain here. So the first one here is pretty much right after the ADCs. You see the pre-decimation spectrum, which is a larger slice of spectrum that contains many signals. So that, for example, that would be everything that's being tracked on sort of the L1 path. And then you can move to post-decimation that focuses in on a specific signal of interest, like GPS L1, or maybe Beidou B1, or GLONASS L1. And then post-filtering is after we've applied any digital filter, like a notch filter or a bandpass filter, if it's been applied to that specific signal. So you'll see some of these spectrum plots later on in the presentation from John especially, and I thought I would help you get your eyes warmed up a little bit for what they look like. And what we've got here on the left in the red line is the pre-decimation that I was talking about, and this is for the whole L1 path. So this would include all of the L1 signals from all the constellations of interest. And then this green line here is focusing in on GPS L1 there. And you can see the sort of the small hump of the CA code at the middle there. And on the right-hand side, what you see in the green line in the background is the same post-decimation view as before, but you see in this example we inserted an in-band interferer here, a pretty clean CW interferer, and this blue line is what comes out post-filtering, and this is what's showing up after the notch filter has been applied there. All right, so previously, when we first launched OEM6 back in 2016, we talked a lot about our mitigation capability, and I just wanted to remind you a bit about those. We've got some publications there if you're interested to hunt them up and read a little bit more about our robust HDR, high dynamic range tracking mode, and the notch and bandpass filters, and how a diversity of GNSS signals can help you survive through interference conditions. So in this webinar, we're going to show you a couple examples of how we've used our own technology on the detection side of things. Try to make it a bit of a behind-the-scenes workshop to show you how you can use the interference toolkit to help solve some typical problems many integrators and users are likely to encounter, but may never really want to admit that they did, and at very least save you some time when you're trying to get your product to market. So I have to remind everybody that prevention is a better cure than any medicine, and being able to characterize your RF environment is a really powerful tool, especially when you're designing, excuse me, a system. The systems today that people are using GNSS in are shrinking in size. They usually include telemetry, data storage, or other additional data processing components. And you're likely operating in an uncontrolled environment that has inadvertent or possibly intentional interferers. So telling the future is a really tricky business, but I'm pretty sure one bet that you can make is that wireless communication and spectrum usage is only increasing and never decreasing, which means interference threats are only increasing and never decreasing. It's never getting quieter out there in an RF sense. And on the same hand, performance expectations are also increasing. People are relying on systems for much more trajectory control rather than trajectory capture, and there's a lot more machine usage rather than human users of GPS. So an interference event that might have been hard to pinpoint that it was actually an interference event, if you had a human there to actually move through it, maybe they get frustrated, give up at the end of the workday, come back the next day and everything's working fine because the interferer's gone away. That's not really going to be so much of the case if you're dealing with an autonomous vehicle that needs to know its position like right now all the time. So yeah, with those increased performance expectations and a more difficult environment in general, there's still no free pass for poor performance because people expect GNSS to just work everywhere. What they're used to and what their perception is, we need to make it a reality. So whatever the threat, whether the threat is inside your system, like what John's going to show us later, or it's outside your system, out in the wild, like Paul's going to demonstrate demonstrate in his presentation, the detection capabilities of the interference toolkit will help you hunt it down, and hopefully pretty quickly. And with that, I'll hand it back to you, General Poss, to introduce our first presenter.
Well, thank you very much, Sandy. I appreciate that. And just before I get on to introducing John, just want to remind everybody we're looking for questions. So ask away using our question interface. And our first presenter is John Schleppe. John is an engineering fellow and manager of research at NovAtel. John has been active for over 36 years in navigation and positioning industry, with 9 years marine and geodetic field operations and 27 years experience in research and development with Pole Search Navigation, Eagle Navigation, and the Plan Group at the University of Calgary, as well as NovAtel. His current research interests are interference and jamming geolocation, and he is the co-inventor of 2 U.S. patents related to jammer geolocation. He holds a master's in engineering and geomatics engineering from the University of Calgary in 1996 and a bachelor's in surveying engineering from the University of Calgary in 1981. So over to you, John.
Thank you, General Poss. I'm very pleased to be here today. Today I'm going to discuss self-interference and how you can use NovAtel OEM7 interference toolkit to identify and help mitigate it. So self-interference occurs when a system's components conduct or radiate electromagnetic signals or the harmonics of those signals into the passbands of your GNSS receiver. This could come from the onboard processors or data loggers in your system, the motors or controllers on your UAV, or the radio or Wi-Fi systems used for data exchange. So self-interference is especially annoying since you take it with you everywhere your system's deployed. If it's present while tracking in clear sky conditions, it can be a real problem when you're in attenuated environments such as under trees, indoors, and especially if you're experiencing external interference or jamming. So Sandy's already mentioned receiver status bit 15 and how it's set during interference events. I'm going to introduce you to the power spectral density graph. Sandy showed you a few examples from that, but I'm going to walk through it in more depth and how you can use it to hunt down self-interference in your system. First, I'll refer to the spectrum plot or as a spectrum plot or a PSD. The power spectral density is a frequency response of the signal, and this graph shows how the power signal power is distributed as a function of frequency. The x-axis is frequency in megahertz on this particular graph, and you can see here this is the L1 and it's from an OEM729. This is 100 megahertz wide. It's set at around about 1582 megahertz. The y-axis on this graph is signal power in dB. We use a fast Fourier transform on the OEM7 to compute the PSD, and in this case the FFT used has 8,192 elements, or 8K. The overall shape of the PSD is really influenced by the filters and amplifiers we used in the antenna receiver. So you'll see a few elements here. First of all, this is our passband here. I'll show it a little bit later. And we filter this sections in here because really we have a number of communication signals in here that are legal, but we want to mitigate them. We have the CA code hump here, and then this information here is the from a mobile satellite spectrum. So the passband refers to the portion of the PSD that has not been significantly attenuated by our filters. I marked it here with a blue arrow. We attenuate the frequencies, as I mentioned before, 1549 and after 1610 because of legitimate communication signals that can affect the receiver's tracking performance. Contained in our L1 passband is, of course, in the red box here, is GPS L1, Galileo E1, and QZSS L1, along with Beidou B1 signals in the green box and GLONASS L1 signals in the blue box. We use the IT spectral analysis command, and I've got it in all caps here, to control the PSD on the OEM7. This command has arguments for mode, so for example, pre-decimation, post-decimation, post-filtering, along with the frequency, so L1, L2, L5, an update rate, the FFT size, and then there's a couple of averaging options. You can request the PSD from a size of 1K to 64K, and at intervals ranging from 50 milliseconds up. So for example, you could display this at, in this case, 8K, 20 times a second. Warning though, these PSD messages can get quite large, especially at 64K, and they'll quickly eat up the bandwidth of your interface, pardon me. I typically leave the PSD off until I really need it. Issuing this command will set up the data collection and processing inside the receiver, and by logging the IT PSD final message on new, you can get the information out, and then in this example, we're plotting it up in a graph in real time. You can see the spectral analysis, IT spectral analysis command in the bottom, and as well I provided a few links to these commands to our online documentation. Now for today, I've decided to pick a smart antenna as my example for self-interference. And I went shopping at the NovAtel's parts bin and decided on 4 main components. Our first component is the antenna element. This one's an element from a GPS 850 wideband antenna. A bit of overkill, but it's got L1, L2, L5, and it's also L-band capable. It's a perfect example because of its wideband nature. And this element is equipped with a 29 dB preamp and as you can see here, a fairly long antenna cable. Our second and main component really is the OEM7 that Sandy showed you earlier. I set up the receiver with all of the constellations, so GPS, GLONASS, Galileo, Beidou, QZSS, and it's also tracking L1, L2, and L5. I've connected directly to the card's header with a 3.3 volt power cable, and a USB 2 cable running to a PC for spectrum monitoring, and a serial cable running to our smart antennas data logger. And for the data logger, I selected the popular BeagleBone Black Linux single board computer. These are really popular with hobbyists, students, people playing around with robotics. This system's packed with the Ethernet, USB, serial ports, got a micro SD drive, multi-pin headers for connecting to all sorts of devices. And also its main job in our system today is to set up the OEM, talk to the OEM729, set it up, and log data from it. It runs on a 5 volt DC supply, and also has a serial cable running from the 729, and there's a power cable running from our power supplies. And the last component is our 2 Texas Instrument eval boards as my power supplies. I went to DigiKey and I picked the 2 lowest cost eval boards that I could find that would that met my specifications. They both run off of a 12 volt battery. I think they have a range of like 9 to 24 volts. And one outputs 3.3 volts for the OEM729. The other outputs 5 volts for the BeagleBone Black. And I purposely picked switching power supplies because I was hoping these would be quite noisy and be one of the sources of my interference, except I was disappointed. They really run quite nice. So you can see the full stack up here. I put together a little carrier and I stacked up my components in this carrier mimicking a smart antenna. You can see the antenna element on the top with the OEM729 below it. And you can see the power supplies underneath the OEM729, followed by the BeagleBone Black in part of its orange enclosure. You can see on the left side there's a black cable. That's the USB 2 cable running to the PC, and the gray cable in the middle, of course, is our external power running into our power supplies. So we have our smart antenna components stacked up and wired up. But before we start, I wanted to show you what a clean band looks like. So that's important. Really, you need to know what you're aiming for so you can go to the rooftop and collect some data, go outside. In this case, I went to NovAtel's roof and I took the actual 850 element that I had along with the antenna cable, the OEM729 I was using, and I separated as much as possible, and then I ran the 729 from a lab power supply and collected some data. So this is what a clean spectrum looks like. You can see the CA code hump, the mobile satellite signals over there, and one slight bump at 1600 megahertz here as well. And the bottom graph here is our smart antenna all stacked up, running indoors. I had a re-rating set up put in my office because it turned the weather turned quite nasty and I didn't want to do this outside at minus 25. I made sure that the re-radiator and my office were not a source of interfere. As you can see, we've got interferers at 1573, 1584 in the GPS L1 band, along with interferers at 1595 and 1600 megahertz in the GLONASS band, and finally interfere on the sort of the upper edge of our passband at 1608. And now we're going to have our first break. Following the break, I'll step through how I use the interference toolkit to help me clean up the L1 spectrum. Back to you, General Paz.
Okay, thank you very much, John. All right, and we're going to go to our next slide and our first round of Ask the Experts. And we've got some really good questions coming in here. And let me look through here, and I am going to ask Sandy. Is there a new version of NovAtel Connect to support the interference status portion of that, and can it show the interference in a time series or some other type of graphical format? That's a pretty technical.
Yeah, for sure. So NovAtel Connect is our PC utility that makes it interface for like a graphical interface for people to see what's going on in the receiver. And yes, there is a new version upcoming of Connect that will be able to give you a better illustration of that over time. So we got your info, Andy. We will follow up on you because maybe you might like to be a beta to evaluate what that looks like before we release it.
Okay, all right, and not so fast, Andy. Andy's got another question here for you. Do the filters preserve phase?
Yes, they do. I noticed that Andy commented there maybe a little bit early to ask that, but I'm always happy to answer the questions from the keeners in the audience. So yeah, when we put a digital filter on or take it off, there is a transition that has to be managed there, but we are doing that on board the receiver for you. So as a user, it should appear to be a continuous phase measurement for you still.
Alrighty, that sounds good. All right, well, John, I got to pick on you at least once here. So, can you detect out of band interference, and what would that look like on a spectrum plot?
Okay, so yes, we can detect out of band interference, and you know, how it would look on the spectrum plot really depends on the size and type of interference. But first of all, the indicators are bit 15 would be set. As well, if you dig into this IT detect status message, it will tell you that you've got an out-of-band interferer in L1, L2, L5, and give you some of the characteristics of that out-of-band interferer. So there's your indicator. And as I said, it really depends. If you've got a large communications channel on one side or the other of our band, it will just start to distort your it will actually just start to distort this the spectrum plot. So that's usually how you see it. But really, the IT detect status message is your best way to go.
Okay, that sounds really good. Okay, Sandy, here's one. Hopefully this is going to be easy. Can the interference toolkit identify the type of jammer I am encountering?
Yeah, John mentioned that a little bit in his previous answer, but yeah, we need to be able to internally identify what type of jammer it is as we work to, picking the right mitigation to apply after that, because not every mitigation technique, what's the right way to put it? There is no one size fits all for mitigation techniques to deal with that interference. So we do a lot of work to identify and characterize what type of jammer that we're seeing and kind of what the signature effects of that type of jammer is. And that's output in the IT detect status log that John was mentioning there, which is in our online documentation if you want to go look it up.
Okay, and I think we got time for one more, maybe. We'll see how quickly this one is. John, real quick, can the OEM7 differentiate between a spoofer and a jammer? And if so, how? And we just got a couple minutes to answer this. We'll see if we can squeeze it.
My answer is short because no, it currently can't detect between a jammer and a spoofer. It would show up as a jammer right now.
Okay, well, there we go. That's an easy one. All right, so that leaves us time for one more. Sandy, real quick, what receiver models is the interface toolkit detection offered on?
All of them, absolutely all of them. I like to say that we'll let you find out you have a problem for free, but when you want to mitigate it, then the model option specifically comes into it after that.
Oh, that's fantastic. Okay, I'm getting the hook here, and that's all we got time for on questions. So we're going to go to poll 2. This is a good one. Which of the following are you more concerned about? Intentional kind of malicious jamming, general wireless communication interference, self-induced system interference, another type of interference not mentioned above, or none? That's a really good selection of questions there, Lori. What do you think?
Yep, sure is. And those responses are coming in. So let's see how they line up.
Yeah, I'm going to go with definitely not intentional as the top result. So I may have messed somebody's responses up. We'll see.
Yeah, I see them changing now as you speak. Damn it. I think they're trying to prove you wrong. All right, let's take a look. There you go.
Yeah, I'll be honest with you. The reason I'm so much against intentional and malicious jamming was that was our first idea was, in the Air Force, people were actually out here doing this, but it turned out bozos with RF devices was by and far the most common one, but I don't know, maybe I'm wrong. Okay, all right, so that was a good poll, and let's turn it back over to John for part 2, so take it away, John.
Okay, welcome back. So before the break, I left you with the L-Round 1 spectrum results from our smart antenna's first design. I was concerned about the interferers on GPS L1 band 1573, 1584, as well as the interferers in the GLONASS L1 band between 1595 and 1600 megahertz. The middle picture of this slide shows my re-rating setup. I had basically a wideband choke ring antenna on NovAtel's rooftop and down through our antenna network, and I had radiated out of this NovAtel 704 wideband passive antenna. I set up the distance here between this antenna and my smart antenna's antenna. It's so that I could closely mimic what I see on the rooftop in terms of satellites tracked and the spectrum. The main thing this setup does is lets me monitor the spectrum in real time. I could watch my PC as well as I manipulated and moved around cables and devices. And so you're looking at the picture on the right, you can see the backside of our smart antenna, and with a few long cables there that I put there on purpose. So the first step to isolating the interference source that I often use is try turning off components. Of course, I couldn't turn off the OEM7 but I could turn off other components. So what I did was I turned off the BeagleBone Black, and this cleaned up the interference on the GPS L1 quite well. On this graph here on the right side, you can see two curves. The black is our initial design with the interferers, and the red is with the BeagleBone Black off. So obviously it looks like it's a source of interference. Since we need the BeagleBone Black to log our data, we're going to have to figure out a better way of getting rid of this interference without turning off the BeagleBone Black. So the first thing most people try to do is shield. So I just happened to have a metal enclosure handy for the BeagleBone Black, so I screwed it on and put the BeagleBone Black back in the stack. As the results show in that we had an improvement at 1573 as well. So the arrow pointing here is at about minus 67 dB. And we also seem to eliminate the interference here at 1584. So this is pretty encouraging, but there's still more interference in the L1 band than I really would like. So next thing I tried was to move the BeagleBone Black around. So I tried it sideways in real time, and I tried it upside down, and it turned out that turning the BeagleBone Black over seemed to be the best, probably because all the components now are facing away from my antenna. And so you can see the indicated interference at 1573 is about minus 75 dB. Finally, I started checking the cables coming out of the BeagleBone Black or going into it. These, as I said before, they're fairly long cables. I didn't shield them on purpose. And so the first thing I tried was actually shielding the BeagleBone Black's power cable. Actually, this didn't make, and I shortened it up. This really didn't make a difference. So the next thing I did was put a ferrite choke on the original power cable and on the serial cable. So a choke is really an inductor that's used to block high RF noise that would be emitted from this cable. You've probably seen them as the bumps on cables from older wall blisters and laptop power supplies. I used a ferrite bead here. On the power cable, I did 2 windings. You can see a couple windings here. And on the serial cable, I did 1 winding. As you can see from the PSD plot, I've pretty much brought the interference down on 1574 to about minus 80 dB. I'm really quite happy. The rest of the interferers in L1 are pretty much gone, but I'm still left with this interferer at 1600 megahertz, which obviously the BeagleBone Black isn't the source of. So how do we get rid of this interferer at 1600 megahertz? I had a feeling this long cable, this 54 centimeter cable, antenna cable, would be a problem because we've had similar difficulties in the past with other designs. So I decided to change to a shorter cable that ran directly from the antenna to the RF cable without hanging down. This reduced the interference at 1600 megahertz from the minus 68 down to about minus 77 dB. I believe the remaining portion of this 1600 megahertz is probably from my PC in my office, since the RAM is at 1600 megahertz. So to wrap this up, you've seen how I use the power spectrum density data from the interference toolkit to isolate and eliminate interference on my basic smart antenna. I did most of my experimentation with the spectrum running in real time at 20 megahertz at a 20 hertz update rate with a 8K FFT. This allowed me to quickly see the consequences as I moved cables and components around. This is a great feature when you or your clients are experiencing problems, such as when you install a system in a new vehicle, a new environment, or you add new components to your systems. As I mentioned before, I don't always run the spectral analysis tool at high rates or large FFTs, but for new systems environments, it's really easy to turn this on, log the data, or get a quick look in real time. Now, throughout this presentation, I've been showing the L1 spectrum plots, and to be truthful, the interference doesn't really look like it's much, and it would be affecting the GPS tracking. So I did a comparison between the carrier to noise density ratios for GPS from my first and last design relative to a clean rooftop antenna. And here you can see, using the interference toolkit, it helped me clean up the spectrum, resulting in a carrier to noise improvement on GPS of about 4 dB. My first design here, you can see there's about a 4 dB drop between the rooftop and my first design. And on the graph on the right, you can see we're essentially cleaned up the spectrum, and it's running pretty much the same as the rooftop. 4 dB doesn't sound like much of an improvement. But the accepted standard in the GNSS industry right now for interference is a drop of about 1 dB. At open sky, 4 dB wouldn't make much of a difference in tracking and positioning performance, but in attenuated environments where under trees, indoors, the presence of strong external jammers or interferers, this can mean the difference between tracking a satellite or that channel going into acquisition or search sky mode. Thanks for your attention today, and I hope you enjoyed the presentation. Back to General Paz.
Well, John, thank you very much. That was a great presentation. Okay, so we're going to turn it over to Paul Alves next. Paul received a PhD from the Department of Geomatics at the University of Calgary in 2006. He's worked for Leica Geosystems, InsideGNSS, and of course NovAtel, focusing on positioning algorithms research and development. He is currently a principal research engineer in the applied research team at NovAtel. Over to you, Paul.
Thank you, General Paz. So I want to start by thanking my Innovation Week team. They really helped me take these ideas and turn them into reality. And I also want to thank 2 people out of our customer service team for sharing their customer stories with me and providing the data that you're going to see in this presentation. This is the original motivation, the reason why I ended up putting together this utility. There was this customer service case in India where the the customer was reporting, for 1 or 2 hours every evening, we would our GPS receiver would stop tracking completely. And they said, this must be a problem with your receiver. And we said, well, there's nothing in our receiver that would stop it from tracking every evening. So we'll send someone out to investigate. And of course, since it only happened at night, Sarah Vanden had to walk around in the dark trying to collect some data. And he identified that using the interference toolkit, that it was in fact an interference problem. And he took this setup that you see there on the right, and he walked around and started measuring power levels, the received power levels from the interference source. And you can see the numbers on the map are the received power levels of the interference source. And he's basically playing this game of hot and cold. So, he walks a couple hundred meters, takes another measurement, says, okay, well, I guess this direction is getting further away. We'll turn around and go the other way. And he ended up creating this map. Now this map makes it, you can interpret the map, like it's possible to look and say, okay, well, this one's -10, it must be close to this. This one's -14, maybe that's a little bit further away. But it's not really intuitive. It's not very easy. And in the end, he did end up finding the interference source. So it was the interference source ended up being this weather station antenna that would upload the data that it would collect it all throughout the day, and it would upload it every night. And in the end, we ended up recommending to the customer that they move the antenna to another building, which they ended up doing, because it's always better to move the interference source. They could have used some of the tools in the interference toolkit to mitigate the problem, but it's always better to remove the source of the interference than continually applying some form of mitigation. So we set out on this project with the goal to find a way to easily visualize the interference, so it's easier to understand where the interference is coming from, what the impact of the interference is, and to hopefully find the source of the interference. Since the interference toolkit gives these nice PSD plots that show the power at different locations in the spectrum, we decided that we would try and use just a simple look at the received power levels in order to estimate the location of the interferer. And we made some assumptions for this first crack at it to try and make it easier. So we assume that the interference source is static, so it's not moving around. We assume that the interference source is continuous, so it's always broadcasting at the same power. And we assume that the gain on the measurements is all the same. So we're not swapping out antennas or cables or using different receivers as we measure around the area of the interferer. So the first thing, since we're using the received power, we need to understand how the power changes as a function of distance. On the left here is the kind of classical free space loss in a vacuum. You could pull off Wikipedia. And on the right-hand side is the power level that we actually measure. Now these don't agree because there's lots of other factors that go into the power loss as a function of distance, especially in this case since this was in a parking lot, so there's other cars and buildings and terrain, things that could get in the way and degrade the power of the signal. So we wanted to make sure that we didn't cherry pick the power loss that we were going to use. So we stuck with the clean classical equation for the power loss, and we went with that. So there's no data cherry picking, and this is okay because we really just want a general impression of where the interference source is. So we start to get an idea of what kind of information we can get from a single observed power. So let's say we're here. This x-axis shows the position. So we're here and we observe some power. And if we assume, let's say that we think the interferer is at this location, then we can use that power curve, connect it with our observed power, and we end up getting this potential transmitter power at this location. And we can continue this, instead assume, let's say that the transmitter is here, again connect this curve through the observed power, and we get a potential transmitter power here. And we can continue to move this around and we get this interestingly shaped curve. Of course, since this is position, we could have the transmitter on the other side of the receiver. And this is an example of just in one dimension. So you can imagine in 2 dimensions, this would look like some sort of sinkhole around, and you'll kind of see that in the plots that are coming up. The point here too is that this gives an infinite number of possibilities for where the interferer is. We could have a low power interferer that's very close to us, or we could have a high power interferer that's very far from us. And there's really no way to know with just a single observation point where the interferer is. But when we start to introduce multiple observation points, then we can combine them together, and the pattern that it creates starts to give us an indication of where the interferer is. So here we have our original measurement. We move, or we take a second receiver and we measure the power over here. And we get these two curves that kind of conflict with each other. And there's lots of different options for how to combine or mix these two measurements together. We wanted to keep it very simple and easy, so we just took the minimum value across all of these observed points. And we can already start to get some interesting information from this. If we assume that all of these measurements are zero, meaning that we don't estimate any interference at any point, then we can create this plot of the minimum detected detectable interference. We could have, this plot shows the lighter colors show higher sources of interference, so higher power interference that could be hiding in our network, and the darker shows lower power interference that could be hidden on our network. So this gives us this nice pre-planning tool where we could say, okay, let's say we want to protect some sort of critical infrastructure like an airport, for example. We want to make sure that we can detect a certain power of interferer within this area. We could use this tool to say where exactly we need measurement points in order to ensure that any transmitter above a certain power will be detectable around the network. And it shows us that, like for example, for this case, we could have a higher power interferer in this area that would go undetected, but in this area, that interferer at that power would be detected. And then we'll move on to try and see if we can find the source of the interferer. So once we have all these measurement points, we have this curve of combined the likely power or the possible power of the transmitter at each of these locations. We create a grid, and we go through each point of the grid and use that power decay curve from that point and do a fit to all of our measurement errors. So for example, from this location, it will fit very well to this observed power point, but it will not fit very well to this power point. And we do this for each point of the grid, and we create this RMS fit error. The other thing that comes out of this that we created was what we call these roller coaster plots. And this is an example from simulated data set, which I'll show you in a second. The height of this graph shows the relative power of the received interferer, the received interference power. So as we drive up this curve and go around the corner, we're approaching the interferer, so the received power gets higher, so the bar gets higher. And as we move away from the interferer driving down the road, the received power becomes lower. So this roller coaster plot also provides a very powerful analysis tool to be able to easily see what the interference looked like across the area. And of course, we started with some simulations because we didn't have any real data at the beginning. This is a couple blocks near our building here at NovAtel. And to start off with, we simulated an interferer here. You can see the roller coaster plot going around the corner, the same that I showed in the last slide. And you can see the bright color is the higher likelihood that that's where the interferer is, and the dark color, the dark purple color, is the lower likelihood that the interferer is there. And the map this method does a very good job. Of course, this is simulated, so there's no noise. There's no noise floor. It's perfect data. It does a great job of identifying where the interferer is. Here's a couple other locations. So on the left, we put the interferer by the road, and we get this interesting kind of mirrored effect where the algorithm can't determine whether or not the interferer is on the north side of the road or the south side of the road. And on the right, here's another example where, again, we get kind of a little bit of ghosting on the outside of the network where we can't really tell the difference between the inside and the outside. And you'll see this in some of the real examples that I'm going to show later on. And just to test our assumptions, remember we assumed that there's just a single source of interference. We did a simulation with two sources of interference just to see what we would get. The roller coaster plot gives a really nice overview of what the interference might look like, and we might be able to just interpret based on the roller coaster plot that there's more than one source of interference. And the map also, it's not great at obviously at locating the interference, but it does tell you that there's something going on in that area that perhaps wasn't before. So let's go back to that case study in India and apply the map that the mapping method that we came up with. Remember, it's really kind of a quick and easy method. We just want to get something that we can easily visualize and get an idea of where the interference source. And this is what we get. And this map, so again, lighter means higher likelihood that's the interference source. I've also located or put a point here of where the interference source actually was. And darker, of course, means that that's a less likelihood. So the map does a pretty good job of visualizing where the interference source, and would have been easier for someone to easily just look at and say, okay, yeah, there's obviously something there, as opposed to looking at all these different numbers and trying to work out, well, is it close to this one or is it far from that one? So let's look at another case. A potential interference source was presented to us, and we decided to take it outside the city. We'd do some experiments with it and see if it was an actual interference source and how much of an effect that might have. This is a device that was purchased online. It's a video transmitter for UAV. So the idea is you put a camera in your drone, and this device would transmit the video feed from that drone down to your computer or your smartphone or whatever you wanted to use to receive it. This particular version broadcasts at 1.2 gigahertz, but once we eventually identified the device and went back to find the manufacturer, they also have 1.5 gigahertz transmitters that I believe go up to 2.5 watts, which would certainly jam L1 GPS. In this case, we're at 1.2 gigahertz, so we're around the GPS L2 band, and we'll see later on that it does do a good job of jamming L2. So this is what the roller coaster plot looks like. The interference source is here. Once again, the height of the roller coaster plot shows more interference. So as we're close to the interferer, we get this kind of high received interference power. And as we drive around, as we drive further from it, the power kind of decreases, and then we go to the backside of this building. The building completely shields us from the interference, and we receive basically nothing. And as we come back around the other side, we start to see the interferer again. There's also a building here on the north side, so north is to the right in this picture. And this building also does a good job of shielding us. You can see in the backside of this building, the received power dips down, and that's really going to impact the plot that you're going to see in a second, the map that comes out of this. And this shows the number of L2 satellites tracked. So now we're using the roller coaster plot to try and analyze what impact the interferer is having on our receiver. So the height of this bar is the number of satellites. So over here we have, I believe, 12 satellites tracked with no problems. And as we approach the interference source, when we get close enough to it, it completely wipes out all of our L2 tracking. And this is what the map looks like. So again, it gives you a nice visualization of approximately where the interferer is. It's shifted a bit to the south, and that's because of that shielding of the building to the north. So because the building to the north is shielding the received interference power, it doesn't end up matching up nicely with that power decay curve that we assumed at the beginning. And because of that, it moved the high probability point in the map further south and further away from it. If we exclude the data from the north, we can see that probability circle shifts northward as we remove that kind of non-fitting data. But either case, for what we wanted as an objective to just give an easy visualization of where the interferer is, I think this does a good job. Between the roller coaster plot and the map, does a great job. The last use case I'm going to talk about today is from Tokyo. So we had a customer that had some problems with interference in the past, and they decided that they wanted to do a pre-survey of a few demonstration routes or demonstration areas just to make sure that there was no interference in those areas for an upcoming demonstration that they wanted to give. And Brian went out there and collected some data, and he did find some interference. So this is what the power spectrum density plot looks like from the entire test that he took. And for those of you that are hard of seeing, the interfere is this large spike right here. So it's very obvious from the PSD plot. And this is what the roller coaster plot looks like, and this is what the map looks like. And based on the report from Brian and the map, we weren't able to confirm it, obviously, because this is out in the wild. There's no way, but we believe that the source of the interference was coming from one of the cars in this parking lot. So that's the end for me. I'm going to pass it over to Sandy to do some final thoughts and wrap it up. Over to you, Sandy.
Thanks, Paul. So today, what we really want you to remember after the webinar today is that it's often an unintentional interference that can create problems for you. But really, it doesn't matter what the intention of the interference is, the effect on your performance is the same. So remember that John showed about a 4 dB drop in open sky there. So that was just purely from how his own integration was done. So you want to maintain the best possible environment you've got that you control for your GNSS performance. It may manifest in fairly subtle ways, but as you move into more difficult conditions, you'll definitely notice things like a much longer time to signal acquisition or reacquisition, or possibly never even acquiring a signal. And then that plays into a longer time to a first RTK fix or a PPP convergence or reconvergence time. So again, I mean, interference is something that when we planned our OEM7, thought was a key concern, and the interference toolkit is built into every single OEM7 receiver as a result. So I'm done there.
Okay. We do have a third and final poll, and we would love to hear from each of you. Would having these options on your receiver influence your receiver purchasing decision? And choices here are interference detection, interference mitigation, both or neither. Okay, let's
Can I
take
say
a
what
look.
All
Oh
right.
yeah, go ahead.
Both, definitely both.
All right, let's see.
All right.
All right.
All right, I finally ace one. There we go. Get the right.
Awesome.
Gosh, who
All
said
right.
either?
I don't know.
Or neither, for where it's at there. In the unlikely event that you've got additional questions after this webinar, there's a bunch of places where you can contact NovAtel for additional support. So if you want to locate previous publications on mitigation, there's an email for that. They have got some great interface mitigation videos and related product info at their website at NovAtel listed. And of course, I know you're going to want to sign up for updates on their excellent NovAtel interference toolkit there at the website at the bottom. Okay, Lori, and I guess we get time for questions.
We sure do.
Okay. All right. The survey says, all right, there's a bunch of good questions out there, and please continue to ask more. Okay. Here's one that I dealt with frequently in my previous life as a signals intelligence officer. John, do we have a way to notch out certain bands in the receiver tracking aside from using external notch filters? I guess, for example, SATCOM and radar have been issues in the past, and is there a way to easily do that?
Yes, we do have the ability to do notch filters and or bandpass filters. Now, if you remember back in my slide 5, I showed the green, the red, and the blue box in our passband. So those are each one of those boxes represents our post decimation, and you can apply notch filters or bandpass filters within those zones. If it's outside of those zones, then no, we don't have the ability to do a notch or bandpass filter. And if it's a really powerful interferer, I really recommend first stage is to actually use a notch filter in line with your antenna, or have an antenna specifically designed for your environment. So for example, for marine environments, we have a design an antenna designed to block out Inmarsat from a lot of the vessels that we're on. So I hope that answered your question.
All right, that sounds good. Yeah, it's always tough to put a band in there for everything. So, okay, who haven't we picked on yet? Paul, we got a good one here. Is it possible to find the direction and the distance of the interference source using your techniques?
So using just a single receiver at a single location that's not moving, I don't know of any ways. I should say using a single antenna at a single source. I don't know of any ways to determine the distance and direction. However, once you start combining multiple antennas, either separated or even within kind of a short antenna array, then there are methods to determine the direction and the distance. As I showed, I was just using the receive power, so you have to either have multiple receivers with this method, or you need to be moving around in order to find the location and distance.
Okay, that's a good answer, and you can get a waiver for everything, but not physics, so there we go. Okay, hey John, back to you. This is hopefully a quick one. Was the antenna cable type changed as well as the length shortened in your experiment?
Yes, that's a great question, and someone with keen eyes noticed that I did change. I cheated. I did change the cable as well. So I think it's the length, but I didn't have a shorter cable of the same type. So I went to a double shielded awesome cable for my later design.
Okay, gotcha. Engineer cheating. We have it on tape now, by goodness. Okay, Sandy, I'm going to ask you one from the heart here. And keep in mind when I ask you this, I was worshipped as a god during Desert Storm because I was one of the few captains out there that had a LORAN receiver. Does LORAN still have a role in providing backup to GPS, or has it been completely shut down? And don't break my heart and say it's completely shut down.
Well, I'm going to start with saying LORAN, can be a backup, but our first priority is to protect the GNSS because LORAN doesn't offer the same type of positioning accuracy that you can get from GNSS. So there's a lot of interest in LORAN in Europe still, and in North America it's diminished because I believe it's been defunded. So it's an alternative to GNSS. It's a separate frequencies, different error behaviors, and it can be used there, but it would require other equipment, right? You generally don't have a GNSS LORAN receiver combined in one piece of hardware because the difference in the frequencies involved there. So yeah, it can play a role, but it depends on where you're operating and what precision you need in that backup and how much money and space you have for specialized equipment. I think that's all the things I can answer about that.
Okay, so you're saying defunded in North America. That's terrible. Wait until the zombie apocalypse happens. We're going to want that LORAN back. I'm just saying.
Well, LORAN's pretty cool because even here in landlocked Calgary, we could receive signals for LORAN, even though it was, kind of meant to be a little bit more maritime. But even up here.
Oh, you're backing me up there. And in Desert Storm, we actually deployed U.S. Coast Guard out in the middle of the desert who were still extremely mad at the recruiters to set up LORAN. So
to be in the middle of the desert.
Yeah, it was not fun. Okay, Paul, can't forget you. Okay, in the Calgary case study that you mentioned, was the video transmitter strong enough to affect the positioning performance of the receiver?
So in our case, we were using autonomous positioning, so no RTK corrections, no DGNSS corrections, no PPP corrections, and in our case, no, it didn't really affect us. Our receiver does a good job of being able to work without needing any particular frequency, so we could have a dropout like that and kind of coast through it, as long as it's not for prolonged periods of time anyway.
Okay, that makes sense. Okay, let's see what we got here. Okay, Sandy, in a UAV application, can the PowerPack 7 internal memory be used for logging data during flight so that you can do post-processing to evaluate any interference?
Yeah. So just for people who don't know, a PowerPack 7 is an enclosure product. So it's a 7700 receiver card inside an enclosure that also has a few extra communication peripherals on it. And one of them here is the onboard internal memory. So yeah, I mean, you can log those interference-related messages just like any other log on the NovAtel receiver. The one thing, though, relating back to what John pointed out, you'd have to be careful to make sure that you balanced how much the receiver, how hard the receiver was having to work to log what you were asking for. If it was the PSD plots, for example, PSD logs that you could then use to make a plot. So just as long as you weren't trying to run at a very high rate or very high resolution on those, you should be able to do it, but it would depend on what the rest of your logging profile was. Like, I don't know, maybe you're running at a 50 hertz RTK solution with span in the background. That's the only thing you'd have to watch for, just balancing the overall loading. But yeah, absolutely, in theory, log all that data for post-processing later on.
Okay, sounds good until you run out of memory.
Yeah, that part too.
Okay, let's see, John. Can the interference toolkit present the spectrum in time domain, frequency versus time? And is it possible to extract the IQ baseband data for analysis and other tool sets?
Okay, so that's an interesting question because it's something that we've actually been working on for a number of years. And it's not specifically the interference toolkit as the OEM7. So we have a feature that's in development. So it's out of research and into the development team that we're hoping to put on our receiver. And it's called Sprinkler. And it's basically a burst of time domain IQ data that you can pull off the receiver for pretty much as you saw, the pre-decimation, L1, L2, L5, or the post-decimation, for example, the GPS or the Beidou or GLONASS, and it outputs a burst of data. So it's not continuous because basically our interface can't handle that amount of data. And so the best way to get a hold of that is to contact NovAtel, and we can give you more information on that.
Okay, sounds good. All right, and speaking of contacting NovAtel, Sandy, is the interface detection in OEM7 different from what is in OEM6, and where can we read more about this, its theory of operation?
Okay, yeah, well, it's hugely different in OEM7 than OEM6. If you are a longtime NovAtel user and are really familiar with those bits in RX status, you'll say, hey, bit 15's been defined as jammer detected for a very long time. And that's true, but we really haven't utilized it much before OEM7, because OEM7, we built in some very specific capabilities to help us do really reliable interference detection, because we don't ever want to be in a situation where, we're crying wolf and we're having too many false alarms to say that there's interference being detected there. So OEM7 is more than an order of magnitude different than our previous generation receivers on what it can do for interference detection. And where can you find out more about the theory of operation on that? Well, you can watch our publications, the ones I mentioned there. But like I said before, interference detection isn't super straightforward. There isn't sort of a single indication of it. And everything that we look at to be able to declare something interference, I think I'm going to bin that under secret sauce or special sauce. And we'll probably never tell you exactly how we do it, because it's been an interesting, challenging technical problem to solve. So yeah, check out our papers that I referenced there. And if you have questions, you can always contact our support line and we'll see if we answer all of them. It depends exactly what detail you're looking for.
Okay, sounds good. Okay, hopefully this is a pretty easy one here, Sandy. Can the interference toolkit be used at GLONASS frequencies?
Yes, absolutely.
Okay, one word answer from an engineer. Who knew? Okay, so here's the next one. Paul, how far away did you have to move the weather station antenna before it did not cause you a problem?
Sure. So one of the reasons why Sarah Vanden actually went as far as he did was to try and estimate how far he needed to move, and they ended up moving it, I believe it was 25 or 30 meters away, in order to make sure that there was kind of no received interference, and the customer they had another facility that they ended up moving it to.
Okay, that sounds good. All right, and who haven't we picked on? Well, John, okay, you mentioned that you run the spectrum analysis tool at high rates for system integration. Are there any disadvantages of running this at a high rate?
Yeah, that's a good question again. There's a few disadvantages to running at a high rate. First is the data volume on your interface. And so that can, the receiver has a basically a management tool that decides if you're going to overload your interface. So you may not get all of your messages across that that interface if you're, say, for example, requesting a 64K FFT at 20 times a second. And so the second one, of course, is that you're drawing on the receiver's processor power. So you have to really be careful balancing between, if you're trying to do RTK or PPP at the same time as you're trying to look at the interference toolkit spectrum plots. You really have to balance that. I recommend doing one or the other. If you're looking at the interference spectrum, just do that, and don't worry about the RTK.
Okay, that sounds good. Okay, I think we got time for one last question here, and John, seeing as how you answered the last question so well, we're going to get you the honor of the very last question, hopefully, unless another really good one comes in. Is RAIM, R-A-I-M, a good option for mitigation interference?
That's an interesting question. I would say it's no, it's not really a good option for mitigation interference. So if you're getting interference, it's going to affect your signals, and some of your signals may or may not fit the positioning solution, the RAIM, and get kicked out. So it's really the best option is to find the interference first and eliminate it. RAIM is sort of your last stage, and that's after we've done all the measurements and we're combining that into the position solution, and we're kicking out bad measurements. So RAIM is actually useful for perhaps some spoofing situations, but I would say it's really the last step for interference mitigation.
Okay, that sounds good. And there's a bunch of other questions. Unfortunately, we're just running out of time here, but not to worry. Trust me, the good folks at NovAtel have sworn up and down that they will answer all of the questions that are in the peak, and there's some really good ones and some really technical ones in there too. Okay, all right. So, Lori.
Yes. Yeah, I would just like to say thank you to each of you for joining us, and trust you found today to be of value, as well as special thanks to our distinguished panel members and, of course, our sponsors, NovAtel, and our co-hosts, InsideGNSS and Inside Unmanned Systems. Again, thanks for joining, and this is Lori Dearman saying, hope we see you on the next one. Have a great rest of the week. Bye for now.